Hello everyone! Welcome to this new deep learning session. So far in this course, we have seen what is a standard architecture of neural networks with the different hyperparameters you need to specify when training a network. Number of neurons, hidden layers, different type of activation function, loss functions, weight initialization, and different ways to prevent overfitting. From now on, we are going to focus on specific neural network architectures. In this session, we focus on convolutional neural networks, which are used to handle images as inputs. If you remember correctly, we mentioned in the first session that backpropagation, used to compute the gradient of the loss for a neural network, was invented in the mid-80s. The first convolutional neural network was designed by Yann Lequin in the early 90s. However, there was not much interest for neural networks from the 90s to 2006, mostly due to computational limitations. In 2006, Hinton et al. Proposed an efficient way to train a network by first training a layer, then adding a layer on top of it, training only this last layer, and repeating this process. The network is then trained efficiently in an incremental fashion. In particular, this is more efficient than training from scratch a whole network because we just have to train one layer at a time, that is, optimizing one set of weights at a time. This new growing interest for neural networks was a result of technical improvements. The first one was the increase of the size of the datasets, since we are now able to collect, store, and manage data more easily than before. The computational power development also helps to build and train more complex neural networks. Compared to these two major changes, more data, more computational power, there were only a few number of algorithmic changes. Namely, the mean squared error was replaced by the cross-entropy loss, and the ReLU activation function was used in lieu of sigmoids. Now, assume that we want to deal with images. Could we use the classical networks we have seen in the previous session? The answer is no, but you can pause the video to think about possible reasons. Indeed, classical neural networks cannot be used to deal with images for two reasons. First, classical neural networks do not take into account the spatial organization of pixels. If the pixels are permuted in an image, the output of the network would be the same, whereas the image will change drastically. Indeed, the order of the pixels and their neighborhoods are really important to understand the content of the image. With classical neural networks, the order of the variables, the pixels, of the dataset is irrelevant to predict, whereas it corresponds to different images. When dealing with images, we want to take into account the fact that the variables are associated with a natural order that we must respect to predict correctly. Secondly, standard neural networks are not robust to image shifting. Assume that we have a uniform background and a cat on this background. If your aim is to detect the presence of the cat, then there is no reason that the classical neural network outputs the same result if we vary the position of the cat on the background. Of course, we would like the prediction of the network to be robust to this shift. We want to be able to detect an object wherever it is on the picture. The idea to solve these two problems is to apply a local transformation to a set of nearby pixels to respect the spatial nature of the image. We repeat this transformation over the whole image, which will result in a shift invariant output. This is not a new idea because, if you remember, the perceptron combines nearby pixels in the first layer. These elementary operations are repeated to extract complex patterns from an image. This idea came from studies about the visual cortex of a cat. Researchers noticed that a cat is able to detect oriented edges and point corners, which are very basic features, and combine them to detect more complex geometrical forms, which are high-level features. From a neural network perspective, we want to create low-level features with the first layer of a network. Then we will add layers that will build on the low-level features in order to create more complex ones to extract information and ultimately detect or not in the output layer the presence of a cat in the picture. In this lecture, we will see what are the fundamental elements of CNN, the convolutional layer, the pooling layer, and some elementary image processing. Then we are going to review the most famous CNN architectures in order to grasp some relevant ideas from these architectures. In the third part, we are going to see more involved applications that are built